what I'm going to present to you today is how to use what has been for years sort of more or less conventional scanning probe technique, atomic force microscopy, and putting a sort of a spin on it. And the spin that we're putting on this technique is to couple it to light and use the atomic force microscope as a tool to bypass the diffraction limit, which normally impedes our ability to see things with light, with conventional microscopy. Use the atomic force microscope as a tool to circumvent the diffraction limit. And then as a consequence of that trick, we're able to see things at the nanoscale, especially in quantum materials, these next generation materials that I'll give you some examples of, that have been impossible to see before. And that makes for a very exciting time to be alive, as it were, in scanning probe microscopy at the advent of implementing multiple different scanning probe modalities, including this nano-imaging technique, all together to probe the nature of these materials. So as Sherry pointed out, I'm at the University of Minnesota, Twin Cities. And just to give you a flavor of where that is, so Twin Cities are Minneapolis and St. Paul, right at the border of Wisconsin and Minneapolis here, and Minnesota, right on the Mississippi River. And here is a picture of our University of Minnesota Twin Cities campus, which is parked right next to downtown, as you can see in this lovely vista right here. And I'm in the School of Physics and Astronomy, which comprises two buildings on the campus here, circled right here, our School of Physics. And our laboratory, the laboratory where a lot of the data that I'm going to show you today was collected, is in the Physics and Nanotechnology building right here on the University of Minnesota campus. And I should also point out, we have world-class clean room facilities here, not but 100 meters away from my laboratory in the same building, which is open for users, and it's absolutely fantastic facilities. And anyone is welcome to visit and bring your projects along with you if you have some fabrication that you need to do, especially if you happen to be in the Midwest area, but we're open to all users. So indeed, so there's a logo for my laboratory. I should point out also that our laboratory has been operating for a couple of years now. So we're still in the early days, but I hope to share with you today some fantastic new results that have been partly enabled by collaboration with Park Systems to enable some fantastic new imaging and nano-spectroscopy tools and capabilities to take a look at these quantum materials. Since I'm a physicist by trade, I'm most interested in probing these sort of exotic materials. So I have to sort of start out by giving you some examples of what I mean when I say quantum materials, because I think not all of us in the audience are physicists. So let me answer that question by giving a couple of examples. Broadly speaking, a quantum material is a material in which you have some interactions between electrons or electrons in the crystal lattice, to such an effect that the material obtains some exotic properties. And shown here is one example of that situation. This is resistance versus temperature for some crystal. It's an oxide crystal. It's a crystal made out of manganese and oxygen. And this particular oxide, if we cool this fellow down, it's a lovely metal. It has a resistance that gets smaller and smaller as we go down in temperature. But this has a peculiar feature that if we turn off a magnetic field, then this material will suddenly become an insulator. Not just any insulator, but an enormously wide band gap insulator. So this is one of the features of quantum materials, is that they're switchable. And this is a perfect example. This is the colossal magnetoresistance phenomenon. And this is the example of manganite crystals. Another example is the Mott insulator. What is the Mott insulator? It's a kind of crystal or a kind of material where electrons repel each other so strongly that they can localize on lattice sites. And instead of having a metal, you instead end up with an insulator. But this is another situation where we can tune which phase the material is in. So this is an example of a phase diagram, and I'll show you another one similar to this in a couple of slides. On the x-axis is pressure, and on the y-axis is temperature. And if you think of something like water, and you tune the temperature of water, you tune the pressure that you apply to the water, you can trigger different phase transitions in water. And the same thing is true for a quantum material like this one. So in our case here, this quantum material has a low temperature phase, which is a superconducting phase. It also has a a insulating phase that can be triggered by the interaction between the electrons, and it also has a metallic phase. And shown here on the color scale here is sort of a derivative of the resistance with temperature. And the funny thing to notice about this particular phase diagram is that it's really quite similar to other interacting systems, including the water phase diagram itself. You can think of the low temperature ordered phase as an ice, kind of like an ice phase of water. And you can think of the insulating phase as a liquid phase. And you can think of the metallic phase as sort of a gaseous phase. And it's really because of the interaction between water molecules that we get ice. In the same way, it's the interaction between electrons that we can trigger an insulating phase for this crystal. Moving on, some other examples of quantum materials. Many of us have heard of superconductors. In particular, high temperature superconductors are a perfect example of quantum materials. We have here, and again, a phase diagram, temperature and concentration of electrons or holes that we can put inside of the crystal. And by tuning these axes, we can control what phase the material is going to be in. It might be a metallic phase. It might be an insulating phase. And let me go ahead and enable my laser pointer. Or it might be an ordered phase, like a superconductor. And unlocking the reason why these phases are stable in different portions of the phase diagram is going to be key to functionalizing these quantum materials, so that we can, for instance, find a way to replace silicon in our transistors with some other material that we can switch, perhaps with less energy loss and higher energy efficiency. Another example of quantum materials are the so-called topological materials. I won't talk too much about these in this presentation, but the point is, topological materials are endowed with special properties owing to electronic states that exist only at their surfaces. So if we have a three-dimensional crystal, the surface might be conducting even though the volume of the crystal is insulating. And that comes as a consequence of the topological characteristics of electron states inside of the material. And the last example that I'm going to be harping on a lot in the last portion of the presentation is this concept of designer quantum phases. A designer quantum phase is sort of like we take a material and we manipulate it in some way until it has the properties that we want. So one example of that is taking a sheet of graphene, which is a one atom thick layer hexagonal a lattice of carbon atoms, as many of us know. And in this particular example showcases the opportunity to turn graphene from a metal into something a little bit more interesting. By illuminating with light, we can open a gap in the band structure of graphene. And suddenly this graphene will conduct electricity, but only at the boundaries of the graphene and not inside of the bulk of the graphene. And not only that, current will only flow in, let's say, a clockwise direction if we try and pass current through this sheet of graphene. And the idea here is, we take a material and we perturb it in some really, really strong way, in this case with an intense light field, until the material reconfigures itself into a state where it has the properties that we want. So this ability to sort of switch materials back and forth is sort of the hallmark of these quantum materials. They're very sensitive to ways in which we might push them into a different phase and thereby control their properties. So one dirty secret about all these quantum materials that I've shown you here is that they're very inhomogeneous at the nanoscale. So one characteristic example in the insulator metal transition, let's say one of these Mott insulators, where, just to remind you, if we tune temperature, maybe we tune pressure, and we can encourage the electrons to interact more strongly with each other and then turn into an insulating phase. Or we can melt that insulating phase by cranking up the temperature. And here's an example of that. One wouldn't necessarily know unless one looked very closely with nanoscale resolution. The transition from insulator to metal for a crystal like this one, this is a crystal of vanadium oxide, goes not smoothly, but goes very inhomogeneously, kind of in a percolative fashion. And so green here is the metallic phase and blue is the insulating phase. And you can see as the temperature is cranked up from left to right, this phase transition doesn't happen smoothly, but happens in these avalanches and these steps. The physics of that would be totally unclear unless we could see at these small length scales. Same is true for these high temperature superconductors, which remain quite mysterious. But what we definitely know about these systems is that not the entire volume of these crystals is superconducting at once. In fact, there's a competition between superconductivity and other phases. And these are some cartoon examples of puddles, of superconducting phase competing with other phases of matter. And these other phases might be charge-ordered regions of the crystal. And as scanning probes have shown, like a tunneling microscopy, the the intensity of the superconducting state, which is in this color scale right here, varies on length scales as small as 10 nanometers or even smaller, because this phase is competing with other phases down at these really small length scales. And when it comes to these topological materials, what makes them special is these electronic states that exist only at the surface. So if you take a two-dimensional crystal, that's a topological insulator crystal. The special thing about this crystal is the electronic states at the boundary. So the boundary is right at the edge of the crystal. And so by using scanning probe techniques, it's possible then to actually visualize these electronic states that are at the edges. And that's what these bright regions show. This is the measurement of the conductivity associated with these edge states in what would otherwise be an insulating crystal. And when it comes to these designer quantum materials, the previous slide I mentioned graphene, and so those of us who are familiar with graphene might also know that if you take two pieces of graphene, put them together, and then you do something special like twist them, you can end up with a new quantum material. So you can design the quantum material. In this case, the twisted graphene, some of us may know, actually turns into a superconductor and also has a variety of other phases that are still being explored. And you wouldn't necessarily expect this, but it comes as a consequence of the fact that we impose some inhomogeneity on the graphene by putting two layers and twisting. So with this small twist angle, there emerges some Moiré periodicity, and that's what's highlighted in this hexagon right here. And so if one takes the scanning probe method and looks very closely at this designed quantum material, we can see with our very eyes how inhomogeneous it is. Over here on the right is a scanning electron microscopy image, and over here on the left is a nano-imaging measurement, not dissimilar from what I'm going to talk to you about, showing that the conductivity, okay, the electrical conductivity of the graphene at these small length scales is very, very inhomogeneous, okay? So that is the story about these quantum materials, is that secretly they're very inhomogeneous, and what we'd like to do is find ways of controlling them. So a couple grand challenges that we have at our hands here, and we need techniques to sort of address these grand challenges. How do these quantum phases compete against each other? You know, which one is going to win? Which one is going to be the stable state inside of these materials? How do they compete for dominance? And very importantly for this, we need to actually go in and interrogate the properties of these phases by themselves. It could be that we have multiple phases inside of the material competing. We wouldn't know unless we can probe them individually. And to do so requires going to nanoscale spatial resolutions to actually resolve the properties of these phases. And I'm going to mention just a little bit about morphologies of these phases, how they compete against each other in some of these quantum materials where we can switch. We can try and tell the material whether it's going to be an insulator or a metal by tuning through the phase diagram. And the morphologies of the domains that show up will tell us something about the physics of this phase competition. And we also want to be able to manipulate these phases at the nanoscale. So how to do that is an open question. Can we engineer new electronic phases with this nanoscale finesse? And this question is connected intimately to these designer quantum materials. That's really what we want to do. We want to engineer new electronic phases or new phases with unique optical properties, let's say, with this nanoscale finesse. I'll talk a little bit more about that at the end of the presentation. And can we resolve these phases at their natural energy scales? And some of the techniques that we've implemented together with the Park Systems hardware has enabled us to push the boundaries of this question. So let me just give you an example of what can be seen with nano-imaging of a quantum material using a scanning probe technique. This is a phase diagram, not unlike the ones that I showed in the previous slides, but what we have here is temperature and we have pressure. And this is a phase diagram for a crystal. It's a vanadium oxide crystal. It's one in which the electrons interact really strongly with each other. I won't talk about all the variable labels inside of here, except to say, broadly speaking, if we put the material under pressure or high temperature, it's a metal. But if we put the material at lower pressure or at lower temperature, we can push it into an insulating phase. And the boundary, we can go across the boundary and see how this phase transition actually progresses and see how we can control that phase transition at that phase boundary right there. So to do this, we would have to go down in temperature, but also look with very high spatial resolution to what happens as we go into this insulating phase. And this happens to be a magnetic insulating phase with Néel order. So the example that I'm going to show you right here is a lovely one that comes from collaboration with a group of Ivan Schuler at UC San Diego, who grows excellent, high-quality films of these fellows. And their plan, or the Schuler Group's emphasis in studying these quantum materials, is to, in fact, use them as a form of switchable memory, or to functionalize these quantum materials for applications like neuromorphic computing and so forth. And so really high-quality versions of these films might be key to next-generation technologies that can find ways to replace silicon that we otherwise find in every single piece of electronics. So, but to answer this question, we have to see how this phase transition actually looks, how it actually proceeds, if we want to be able to control it. So if we take a look at the resistance of this film as a function of temperature, we go to low temperature and we get a nice insulating phase. We go to high temperature and we get a nice metallic phase. And in between, we have a transition. And we have a hysteresis here because this is the first order transition. And so there's several questions to ask here: is what's happening in this middle zone where we're somewhere halfway between metal and insulator? And also, what controls the width of this transition? It's not very sharp, or maybe it is. We just have to go in and see. So in order to investigate this material, or this quantum material with high spatial resolution, we use a scanning probe technique. And I'll tell you more details later about how the scanning probe technique works, but it's based on an atomic force microscope, which we illuminate with laser light. And as we illuminate with laser light, and we can collect the scattered laser light, that gives us a probe of the optical properties of the material. And so the optical properties that we're interested in right here is how well does this material conduct electricity? How well does it reflect light? And that'll answer for us whether we're insulator or metal. And so we're going to cool this fellow down and take a look at how this phase transition looks. So here's an example starting at high temperature, maybe in a 50 by 50 micron field of view on the surface of this film, just sitting at room temperature. And here we are mapping the optical conductivity of the film, and you can see that it's all red. That means that we're in a nice metallic phase. But you can ask what happens when we start cooling. So we're going to cool the material down, and we're going to cool it through its phase transition. And so as we cool it down, you're going to see on the left panel here what the instantaneous resistance of the film is as we approach this phase transition. So it's a matter of following the bouncing ball here. And as we start cooling this fellow down, let's say 170 Kelvin, so that's 100 degrees Celsius below room temperature, we begin to see something interesting happen, is that we're triggering the phase transition in this material. And the phase transition happens first in small little regions, and then these small little regions that have lower conductivity begin to grow and then connect to each other and sort of eating away at the metallic phase. Or maybe a better way of visualizing this, we're sort of freezing the water, as you like. We're freezing the electrons inside of the material so that we obtain insulating regions where the electrons have sort of crystallized on their lattices and can't conduct electricity anymore. And so here we are cooling further and further down, and we can see how this phase transition proceeds. Oops, I need to go forward, not backward. And before too long, you can see that we've more or less triggered the entire phase transition. And what's left is just some little remaining regions that happen to remain in the metallic phase. That's what these whiter and redder regions are. Those are remaining metallic regions. And then it's not until we cool this fellow way down that we can see we end up with a nice, lovely insulating state. So what we can see here is that the phase transition is not uniform, right? It's controlled at the nanoscale by things like defects or strain inside of the crystal, or other inhomogeneities that control the way the phase transition actually proceeds. And so understanding what are the reasons why the phase transition happens in one way versus another way at the nanoscale is going to be key to us unlocking the functionality of these quantum materials, especially if we want to use these quantum phases for different applications, especially in switching, memory, neuromorphic computing, energy storage, etc. So what I've just shown you here is a nice example of using nano-imaging to uncover something that hadn't been seen before. But you might be a little bit puzzled, and I think you should, because those images that I showed you were resolved at really small length scales. But at the same time, we're using light in order to collect these images. We're collecting the optical response of the material. So if indeed it's the case, we have some inhomogeneous phases inside of a material, and we have all these questions that we can ask. What are the properties of these phases? What's the band gap in the insulating phase? What's controlling the phase transition, and so on? Well, if we want to use light to answer these questions, we want to probe the material with light, especially infrared light, which is what is the energy at which we're probing the conductivity in those images, you should be a little bit puzzled, because if we try and focus infrared light, many of you may know visible light has wavelengths of hundreds of nanometers. Infrared light has wavelengths of microns. And of course, you could go further in the electromagnetic spectrum to radio and so forth with meters, centimeters and meters sort of wavelengths. But infrared light has micron scale wavelengths. If we try and focus that infrared light, we anticipate we're going to get an infrared spot size about as big as this. How on earth are we going to use infrared light to examine the properties of these phases? And what we're talking about here then is the diffraction limit. Okay, so we can't focus or resolve any finer than the wavelength of light. And those of us who have studied optics know who to blame. It's Ernst Abbe who I should say, discovered this phenomenon back in 1873, and it's inscribed at a memorial to him at University of Vienna. This famous formula of his, Abbe's resolution formula. It's saying that we can't focus these light waves to a diameter d any smaller than the wavelength, that's lambda, divided by the numerical aperture of our lens or our objective if we're using a lens to try and focus the light. And it's uncommon to get a numerical aperture smaller than 1. So how on earth can we focus light smaller than the scale of the wavelength? Well, the truth is this is Abbe's diffraction limit, which is true for propagating light waves. And what is a propagating light wave? Well, it's a light wave that has a wavelength lambda, or has a momentum q, which is 2 pi divided by lambda. That's less than the frequency of light divided by the speed of light. So for any such propagating light waves, Abbe's diffraction formula holds. And this has been the limitation for conventional microscopy with propagating light for a long time. And I love this quotation from Physics Today in the same year that the Nobel Prize in Chemistry was awarded for the development of super resolution imaging techniques in biology. And the reflection went as this: it's a true statement. Starting from Isaac Newton's use of a prism to look at the spectrum of sunlight, our optical and spectroscopic techniques have truly remained fundamentally unchanged for centuries. That is, until the advent of super resolution imaging. So I should say then a little bit about how we perform this super resolution imaging to beat the diffraction limit. And so one way of addressing this question is to think about one of those images that I showed you. So one of these images that I showed you is sort of a map of somewhere in the middle of the phase transition, a map of the optical conductivity of our quantum material. And in some regions, we have the phase that we want. And in other phases, we have the competing phase, or in other regions, we have the competing phase. So this map of optical conductivity tells us which phase is which inside the material. So this is the conductivity, sigma, which is a function of position. But I'm going to do something funny for you. I'm going to take this map, okay, which is maybe 20 microns on the side, and I'm going to Fourier transform it. And instead of looking at the conductivity in real space, we're looking at the conductivity in Fourier space. So as a function of momenta in the x direction and in the y direction, we have the Fourier transform of the conductivity. And so one way of thinking about interaction of light with material is, first of all, to draw a cone, which is called the light cone. And this light cone is defined by momenta that are equal to omega over c. And so we have 2 zones. One is inside this light cone and one is outside the light cone. And the vertical axis here is the energy of light. So we can send in different energies of light that we want and have them interact with the material. And the difference between being inside the light cone and outside the light cone is this: inside the light cone, these light waves will propagate freely, maybe into our camera or into our eyeball. Okay, maybe we use a lens or an objective in order to collect these light waves. And here, the diffraction limit will apply. So the best that we can do with these propagating light waves, the only ones who will propagate are those that sit inside of this light cone. So what happens outside the light cone? Do we not have light? No, the truth is we still have light, but it just happens to be evanescent waves. These are not propagating light waves, but these are waves that die away into space exponentially. So these evanescent waves, as you can see, might have more information content out at these higher momenta. They might have higher spatial resolution information. Well, so if we do an experiment at, let's say, really high energies, then we have a lot of momenta that sit inside the light cone. So if we send these light waves down to the material and they interact, then we can sample a huge range of momenta. So 25 electron volts is maybe ultraviolet light. So maybe if we used an ultraviolet camera then we could see this high spatial resolution information. But then if we go down to visible energies, then things begin to be blurred. And this is because of the diffraction limit. And if we go down to the energy scale at which these phases are really actually different from each other, which is down in the infrared, there's absolutely no way, because we don't have enough information content inside of the light cone. So diffraction kills us. We can't see anything. So we definitely have to bypass the diffraction limit. And the way to do this is one way to do this is to use a near field probe. That is to say, find some eyeball that can go close enough to the material that it can collect these evanescent waves. And if we can collect those evanescent waves, then we can resolve all this high momentum information, that's high spatial resolution information out there. So that's one way to beat the diffraction limit at any wavelength, really. Illuminate with this kind of light and then collect these evanescent light waves. And then maybe we can beat the diffraction limit. So just a little bit of history, and I'll go through this quickly. This idea has been around for a long time. It was kind of invented or suggested way back in the late 20s in a letter that was written to a famous physicist by this fellow, Edward Singe, who suggested that if we take some sort of probe, an aperture probe, and we coat it in metal, and then cut off the metal from the little end, we'll make a really tiny aperture. So then what happens if we send light down through this aperture? Then we can illuminate a region using light that is confined to this really, really small volume. And then we might be able to see with higher spatial resolution. Now, the truth is this letter that Singe wrote to a famous physicist arrived at the doorstep of Einstein, who, although Singe said, I don't think that such an idea would be beyond the capacities of a clever experimentalist. But Mr. Einstein was very suspicious and suggested that it might be way too cumbersome, maybe even impossible to pull off. And so Singe came up with a slightly different idea. What if we take a little nanoparticle instead and illuminate the nanoparticle with light? And what if we bring that little nanoparticle close to some region that we want to image, maybe scan it around? And then if the light waves are only scattering off of this little nanoparticle, which is very small, then we might be able to bypass the diffraction limit in this way as well. And Einstein was a little bit more supportive of that idea and suggested that Mr. Singe write an article to publish his proposal, which also came out in the late 20s. He suggested this method offers itself a little outside the beaten track of microscopy, but raises technical problems of a new kind, and that's an immense understatement. But he supposed that it might be able to give spatial resolutions as small as 0.01 microns, that's 10 nanometers. And it wasn't until much more recent days that this crazy idea was brought into implementation, first by work of Dieter Pohl and co-workers who you actually tried to use a little nanoparticle to scatter light. And what they found is if they brought that nanoparticle really close to a surface, the amount of scattered light would increase exponentially. In fact, what they're seeing here is that this little nanoparticle is actually managing to scatter light out from these evanescent light waves. And that's very exciting because it suggests that we might be able to use this nanoparticle for super resolution imaging. And then later on, folks like Kumar Wickramasinghe at UC Irvine developed different techniques to detect these light waves scattering off of the sharp probe. And Mr. Kumar also took that nanoparticle and swapped it for a sharp needle, and not unlike the kind that we would use for atomic force microscopy. So now we're getting closer and closer to a real scanning probe technique. And then later on, groundbreaking work by Hillenbrand and Kyleman found ways to suppress the background and isolate just the portion of light that is originating from these evanescent waves that might be at the surface of the material. And using actually an atomic force microscope probe to scatter these light waves out enabled really high performance imaging, where we can now, or they did back in 2000 already, notice the difference between different kinds of materials down at length scales as small as 10 nanometers. So here's silicon, and here's polystyrene, and here's gold, and you can see the contrast that's coming from the optical properties of these materials. And then later on, interferometric techniques were implemented in order to not just resolve the light waves that are scattering out from the sharp end of the atomic force microscope probe, but also to resolve both the amplitude and the phase of the scattered light. And that's very powerful to determine what the optical properties are quantitatively of materials like these. So this interferometric detection of these light waves. So nowadays we're left with a technique that looks a little bit like this. So this is called apertureless scanning near field optical microscopy, or scanning near field optical microscopy or SNOM for short. I like to just call it nano-infrared imaging. And so the idea is this: if we have some inhomogeneous material, maybe it's chemically inhomogeneous, maybe it's a quantum material. If we bring an atomic force microscope probe down to the surface of this material, and if we illuminate with light, then what's going to happen is that this illumination will polarize our probe. And let me give a little zoom in there. What does it mean to polarize our probe? Well, if we have our atomic force microscope probe and it's coated in some metal, then the probe kind of acts like an antenna for the incoming light. And the antenna will polarize. That means that we'll get something like a dipole moment inside of our probe. So here's an instantaneous snapshot of charges. So we might have a plus charge on the top of our probe and a minus charge at the bottom of our probe, and this will cycle back and forth as the light wave that comes in is driving this dipole up and down. And if we bring that dipole close to a surface, then the surface will respond by also polarizing, like a mirror image of the probe. And now we have two dipoles. One is a real dipole and the other is an image dipole. And these two dipoles can interact with each other through near fields, these evanescent waves I talked about before. And so I'll spare you the details, but it's a couple of lines to write a simple equation that describes the relationship between the reflectivity of the material. And this reflectivity might be written in terms of the conductivity, or it might be written in terms of the permittivity. But at the end of the day, we find an expression for how polarized our probe is. And the truth is, it scales with how intense our light field is. That means to say, if we crank up the power of our laser, we get more polarization of our probe. But also, if we bring our probe close to a surface with reflectivity, then this polarization changes dramatically, because you can see the reflectivity is inside of this formula. And this is due to the near field interaction. So this is just a very simple sort of expression, but it tells us how much light is going to scatter off of our probe. How much light scatters off our probe depends right on this polarization right here. So if we collect that scattered light in a detector, and if we map that scattered light while scanning the probe around the surface, okay, then we might gain some sensitivity to the local optical properties of the material. And so the idea here is that the scattered light field encodes the local sample properties, the sample optical response, maybe it's the permittivity, down at a spatial resolution of the sharpness of our probe, which can be as small as 20 nanometers or even sharper. It really just depends on how sharp the probe is. And so as a consequence, here's an example of a map of that scattered field as a function of position on some chemically inhomogeneous material. And you can see that some regions light up and other regions are dark. In some regions, there's a strong near field interaction. In some regions, there's not a strong near field interaction. So this is basically a map of the strength of those evanescent fields at the surface of the material. And the truth is, this is a picture, all small, you can see 10 by 10 microns, of a slice of a meteorite that was collected from Earth after it landed in the Australian desert. And this tiny little slice of this meteorite shows a lot of chemical inhomogeneity. And the reason why I say that is because we're illuminating here with infrared light, and infrared light can excite different vibrational modes of different chemical compounds. So in this particular example, if we measure how bright these regions are in the near field as a function of laser energy, and that's down here on this fell out of the way. Find a way to hide this. There we go. As a function of energy, down here on the x-axis, we can scroll the laser energy, and we see at some energies, this little region A will be bright, and at some other energies, this region D will be bright. And this is mapping different vibrational modes inside of the material. And these different vibrational modes allow for chemical fingerprinting. So these are different mineral phases. This is magnesium oxide, this is a glass, this is an albite, which is a potassium oxide. So it's a very powerful way of then doing chemical diagnostics. We're just basically mapping the properties of nanoscale regions, optically mapping those properties at these high spatial resolutions. Okay, so how do we actually do this technique in practice? And it is, in my lab anyway, connected to a Park Systems atomic force microscope to implement this technique. And so the way that it works is first we deliver some light. In our case, we use a pulse laser, which can be tuned from visible, near-infrared, mid-infrared. We deliver this pulse laser to a beam splitter, and we split the beam into two pieces. And those two pieces go into two arms of an interferometer. I won't say much about that until I finish the rest of this animation right here. And then these two beams that were split get delivered ultimately to our microscope. So you can follow these two beams, and you see that one of these two beams is ultimately going to be delivered to a focusing optic, and the other of these two beams is going to be delivered to a flat mirror. And the focusing optic will try to focus that light down to the apex of our little probe, our AFM, atomic force microscope. And this here in the blue box is a Park Systems NX10, which we're calling, when equipped with this optical hardware, we call it the Park SNOM, or the Park Scanning Near Field Optical Microscope. And so this focused light, when it scatters off of the probe, or when the probe out scatters these evanescent fields, then those evanescent fields will scatter back out into our interferometer, and we can collect the interference between our reference beam and those outscattered fields as they recombine through this beam splitter right here at a detector, a fast detector. And by scanning the probe around the surface of the material, of course, and measuring that scattered field over here at the detector, we get a very high sensitivity measurement of the optical properties of the crystal, or of the material. So here's kind of a picture of what that looks like at the business end here with the atomic force microscope. So here in blue, you see a Park Systems NX10, which we've equipped to accept light beams. So here's our reference beam, and here is our optical pulses that get focused down onto our sharp AFM tip. And so if you look, for example, through the camera here, you can see bright light scatter off of our probe. That's from a pilot visible beam that tells us where we're delivering the light to the probe, telling us we've got a good focus onto our probe right there. And in this case, maybe this probe is imaging some little device of a quantum material that's hooked up with some electrodes, and we're measuring the optical properties of this really tiny little device using this near field optical microscope. And so as an example, measuring a little tiny quantum material, maybe it's a two-dimensional material, like a two-dimensional semiconductor in this case, we can both map the optical conductivity. These are multi-layers of this 2D material, and simultaneously measure other properties like the surface potential using, for example, Kelvin probe microscopy. So it's nice to have all this in the same package. Same time as we're mapping the optical response of our inhomogeneous materials, we can also use complementary scanning probe techniques like electrostatic force microscopy, piezo response microscopy, and so on, all in the same package. So that's very powerful for probing the properties of these materials. And here's just a slightly closer view where you can see the focusing optic that is in charge of focusing that light down onto the atomic force microscope probe, which is pictured right there. So that's a closer view inside of the Park SNOM right there. And I should also point out that this implementation allows to do both imaging and spectroscopy. So these are some images, and I showed you quickly before an example of spectroscopy. So how do we actually do the spectroscopy? It depends on coupling this microscope to a broadband laser. So here's an example of a broadband laser that allows to access various energy ranges from the mid-infrared all the way into the visible range, let's say hundreds of nanometer wavelengths to 20 micron wavelengths, and this laser is tunable. So because it's tunable, we can sweep across energies and collect the response of nanoscale materials with energy resolution. So here's an example of that. So a little cartoon showing the atomic force microscope sitting on top of an inhomogeneous quantum material. These bright features are showing the local optical conductivity that's measured with this scanning probe of an exfoliated graphene multilayer. So graphene can be monolayer, it can be bilayer, it can be three-layer. And so here we have just a Scotch tape exfoliated piece of graphene with a variety of different layer thicknesses, and all of them have a different optical conductivity. All in the same picture you can see here in this map that's acquired with the scanning probe. So then what we can do is switch from the imaging mode to the spectroscopy mode and measure the conductivity of these graphene multilayers now as a function of energy. And that's what's scrolling right here. And you can see from low energy to high energy, the optical contrasts change selectively in different regions of the material. So this is the intensity of the reflected light from the material, and this is the phase or the absorption of the reflected light, or absorption of the 2D material. And you can see that the absorption is high at certain energies in certain regions, and the absorption is low at other regions and at other energies. And what this is showing is that different multi-layers of graphene have different optical properties. Some of them have strong absorptions at certain energies owing to, let's say, interband transitions, and others are strongly absorbing due to free electrons or plasma resonance in those materials. So with that example, teeing up some opportunities to showcase what we can see in two-dimensional quantum materials. Let me say a little bit more about these two-dimensional quantum materials. So I was just talking about graphene for a moment there, which is an example of two-dimensional metal. And there's also two-dimensional materials nowadays that are ionic insulators, like boron nitride, for example. And there's also two-dimensional semiconductors out there. And nowadays, even two-dimensional superconductors. And these two-dimensional superconductors can be as thin as a monolayer. And there's also two-dimensional magnets. So this is quite exciting time to be a material scientist because of the advent of all of our favorite materials are now available in two-dimensional form, in the form of these different crystals. So wonderful thing about these 2D materials in terms of their optical response, I'll call them quantum materials because as a consequence of the confinement of electrons to a two-dimensional layer, the properties of these materials are quite different from their three-dimensional counterparts. So in the two-dimensional metals, like graphene and also these two-dimensional superconductors, if light interacts with these two-dimensional materials, what we end up with is a plasmon mode. So these two-dimensional materials are exciting in no small part because this interaction with light enables to actually confine light to the two-dimensional surface. And so this plasma excitation inside of the two-dimensional metal, as it's coupled to light, it actually confines light waves so that they propagate only along the surface because they're strongly coupled to the excitation of this two-dimensional material. And that is the surface plasmon in the case of these two-dimensional metals. On the other hand, there are, for instance, excitons and vibrational modes or phonon excitations inside of these ionic crystals. And in this case, those excitations of matter can give rise to what are called phonon polaritons or exciton polaritons. And what I'm showing you here is what's called the dispersion. What we have is energy on the y scale and we have momentum on the x scale. And momentum is 2 pi divided by the wavelength. And so if we take one of these 2D materials and illuminate it with light, then light waves can be caught and confined close to the surface and will propagate along the curve, the dispersion curve here, where there are allowed modes along the surface. So the surface polariton, for instance, is showcasing high momentum. That means high confinement of the light wave to the surface. And this is very interesting because by combining these 2D materials in different heterostructures, it's actually possible to manipulate this dispersion curve. Let me put that a different way. For a given energy, it's possible to manipulate what wavelength the light will actually have as it's confined on the surface of the 2D material. And by playing Legos in this way, we can not just control the bulk properties of this heterostructure, but also control the optical properties of this heterostructure. So this idea has been around for quite some time, this idea of a polariton. And let me just say a little bit more about what it is. So going back to the 50s, work by Huang and Hopfield, answer the question, what happens if you have an excitation of matter at some energy? Okay, maybe it's a plasmon or maybe it's a phonon. And that exists at one energy right here for all momenta. And 1 over wavelength is the momentum, and that's on the x-axis. What if we couple this excitation of matter to light waves, and light waves have this dispersion, which is slope that has a slope equal to the speed of light. So that's frequency divided by momentum is equal to the speed of light. And if these two excitations interact with each other, which in fact they do in these materials, then what we end up with is a splitting and consequently 2 different polariton modes. That's these solid curves right here. And the exciting thing about especially this bottom polariton curve is that it really tightly confines the light wave. So over here is an example of a 2-dimensional material. It's boron nitride. It's an ionic crystal. And a tiny little flake of this crystal that's maybe 10 microns in size. If we illuminate with laser light at different energies and map the electric field, we can see that the electric field has these waves. And this is in fact showcasing the polariton mode as it propagates inside of the crystal of boron nitride. And this is just one example of these polariton modes. So I'm going to tell you a little bit about imaging the properties of these polariton modes in a quantum material that's graphene, monolayer graphene, which has this sort of plasmon dispersion. And you might ask, how on earth are we going to actually visualize these? Well, the answer to the question is, if these light waves are so high momentum, they're basically evanescent waves that manage to propagate along the surface, we have to use a super resolution imaging technique to see them. And that's where the near field microscopy comes in. So here's our lattice of graphene. And the idea is that if we illuminate with light and polarize our sharp probe can actually launch these excitations in the graphene and can also pick up their electric field to image them. So if we put some electrons inside of the graphene, then we can both excite and also image these modes as they bounce around inside of the graphene. So here's kind of an example, a cartoon image of what's happening here. As the light field from the tip excites these modes, they propagate outwards like a cylindrical wave. And in early days, imaging pieces of graphene that were exfoliated with Scotch tape showed some really lovely images in the infrared, which had some fringes in them, what seemed to be like waves of some kind. And it was unclear at the time, way back when, what actually we're seeing here. What's the physics behind the generation of this interesting pattern, and how is it connected to the polariton that's propagating? So the answer to that question comes from visualizing the probe and the boundary of the graphene as kind of like an echo chamber. So if the probe launches a plasmon mode that goes out and reflects off the edge of the graphene, that plasmon mode will then come back to the probe. And if it comes back to the probe, then it can outscatter and we can detect it. And so in this way, as the probe gets closer and further from the edge of the graphene, we either reach situations of constructive or destructive interference between the light field from the probe and the light field from the plasmon. And as a consequence, we get these fringes that develop, which is a direct measure of both the wavelength of the light or of the polariton and also of the lifetime of the polariton. And so in this way, the quantitative dispersion for plasmons inside of graphene is controlled by a lot of different things. But broadly speaking here, you can see that we have a dispersion where the wavelength of the polariton gets smaller as we go higher in energy. The momentum gets higher as we go higher in energy. And by illuminating with a laser at different energies, okay, we can select which polariton mode we're going to excite and which polariton mode we're going to image. And the properties of this dispersion, the 4/2 max and so forth, tells us something about the lifetime of the polariton and also about the propagation length of the polariton. And I should point out that these polaritons are really exciting because it's not common that you can confine light waves to a small volume in the same way that we confine electrical currents to small circuits. So if we can confine light waves to small volumes, then we can engineer actually circuits for light on small length scales. And what's key to that is harnessing the properties of these polaritons and also controlling the properties of these polaritons. Okay, so I just want to show you one more example in the case of graphene. So what do these plasmon polaritons look like in graphene that's really high quality? And for some years, these quantum materials have been made better and better by making them cleaner and cleaner. And in the case of graphene, that can be accomplished by encapsulating in some protective layers. And then also electrical connections can still be added to the graphene to control it. So this is work by Lei Wang dating back to 2013. And what's shown right here is a lovely sort of fringe pattern at the edge of graphene, the intensity of the light field as a function of position of a nanoprobe to the edge of the graphene. And you can see that there's a lot of fringes that can be seen here, which measures the lifetime of the plasmon or the quality factor of the plasmon, which can be pretty high for these clean graphene layers. So what we decided to do then is to see how far these plasmons can really propagate by using our sharp nanoprobe and imaging them, not just while tuning electrical currents or electrical voltages to the graphene, but instead tuning temperature. So by cooling the graphene down, we can actually see the plasmons propagate for many, many tens of microns. And this is a consequence of the fact that the plasmon lifetime becomes very high. We can image that directly using the scanning probe technique at low temperatures. So here's again, the idea is that we illuminate with the infrared light, and then the probe, the sharp probe, is then capable of launching these plasmon modes. What do? They bounce off of the edges of the graphene, and then they come back to the probe, and then they outscatter. And light waves also can excite plasmons that will propagate from, let's say, sharp objects like gold structures that we put on the surface, and the light field associated with those plasmons can also be seen by the tip. All we have to do is measure this outscattered field to get a sense of this local electric field from the plasmons on the surface. So here's what happens as we cool down the graphene, and what's showcased right here is the profile of the plasmonic electric field as it's launched away from an edge of some sharp gold. And you can plainly see that the lifetime of the plasmon gets higher and higher and higher as we go to lower temperature. So the plasmon has a higher lifetime because at lower temperature, it's not scattered by thermal fluctuations and phonons inside of the material as much. So this definitely demonstrates that down to liquid nitrogen temperatures anyway, plasmons can propagate inside of a graphene layer, inside of a graphene circuit for many tens of microns. And that's very powerful because it means that we can now engineer these graphene layers potentially into circuits for light. So that's ongoing work, which I'm going to spare you. And you'll have to hear the next webinar for that, I suppose. Now, I want to conclude here by showcasing some more recent data on a two-dimensional material that we made from scratch. So graphene is something that you can get from a piece of graphite. You use a Scotch tape, and you can isolate a single atomic layer of graphene. But for other materials, it's not so easy, but it is still possible to take, for instance, a three-dimensional material like strontium titanate and turn it into a two-dimensional material. And I should say that like was the case for the vanadium oxide, where we can switch between different phases, this titanium oxide also has different phases that we can switch between, not just with temperature, but also with applied strain. That's like applied pressure. And so this is a cool material because it has a variety of different phases. For example, if we dope this material, we end up with an unconventional superconductor. Also, if we apply strain to this material, we turn it into a ferroelectric material. And a ferroelectric is one where if we apply some electric field, we can switch the state of polarization of the material in such a way that we end up with some built-in polarization. And that can be used as a switchable memory. It can be used as a source of nanoscale electric fields. And there's suggested to be some strong interplay between ferroelectricity and the origins of superconductivity in this material. And all that remains unexplored, but it definitely suggests that if we can make a two-dimensional material out of this three-dimensional one, we can supply even larger strains. We can bend and twist this material in new ways in order to probe these physics, and also to employ it into a nanometric, let's say, storage for memory by using this ferroelectric transition. So our collaborators at University of Minnesota, Bharat Jalan and his student Shivashish, have developed this absolutely fantastic method to take these oxide materials and grow them with molecular beam epitaxy, but not just grow them on top of a substrate, grow them on top of some sacrificial layer, which is like a rock salt layer, a rock salt layer that can actually be washed away with water, okay? And then by peeling away the top membrane, or what was originally a film and is now a membrane, that membrane of the strontium titanate, in this case, can be put now onto any sort of substrate that we want. Maybe it's an electrical substrate, maybe it's a strain substrate. So this is very powerful. We can take these originally three-dimensional quantum materials and now design them into two-dimensional materials. And it's very tough to examine the properties of these new two-dimensional materials because, of course, they're nanoscale. And nanoscale techniques like transmission electron microscopy do show that the structural properties of these membranes are pretty good. The crystallinity is very high. The atomic lattice is very clean, as you can see in some of these images here. But we wanted to probe the optical properties of these two-dimensional membranes. And to do that, my student Liam Thompson did some investigations using our near-field imaging technique. And so here's the idea, just to reiterate. We take one of these clean oxide membranes that is removed from its sacrificial layer and put on a substrate that we want. And these membranes can be really large as a centimeter on the side, which is pretty fantastic. And the crystallinity is super good, as one can see from these diffraction measurements here. So we're in a good state in order to look at the optical properties of these membranes. So here's an example, putting one of these membranes on the surface of silicon and then probing the optical properties of this membrane. Shows us what the reflectivity is in the infrared and also what the absorption is in the infrared. So this is a little multi-layer of membrane. It's got a little bit of a fold in it. So this is the intensity of the infrared reflectance, and this is the absorption of the infrared light as a function of position. And again, these measurements were taken with our Parkes nom, just at room temperature. So this 15 nanometer layer clearly shows some strong contrast in the infrared. Where on earth is this coming from? The answer is that we have here an optical phonon inside of the strontium titanate layer, which we can excite selectively using the infrared light. And this gives us a handle to probe the optical properties and also the crystallinity of the layer. And so if we take a couple of positions, let's say this double layer and also the single layer on the membrane, my student Liam did spectroscopic measurements mapping the optical properties of this membrane as a function of energy, showing very clearly, resolving in its entirety, the phonon excitation. And so that's what this peak actually is. And that's the origin for this absorption in this narrow energy range, is the phonon inside of these layers. And so the fits to these experimental curves are using bulk optical constants of strontium titanate. And that sort of tells us we have here something that is really genuinely like bulk, like a three-dimensional material, but in a two-dimensional package. And that's really exciting. So my student Braden is taking these studies into the next level, I guess I should say, because we noticed that if one peers really closely at these two-dimensional materials, okay, these two-dimensional membranes, particularly right close to the edge, you can see something really funny. It looks like those fringes that we saw in the graphene plasmons. And we have to zoom in very closely in order to see. So what might be going on here? We have a phonon in the strontium titanate. And the truth is, if we have a phonon, the optical permittivity of this strontium titanate layer has a region where it's negative. And this is what we need in order to have the possibility of one of these polaritons. So this is the question. Do we have a polariton actually in these two-dimensional membranes? And so by doing a quick calculation, there's a prediction here that we should have a polariton wavelength that goes anywhere between 100 nanometers and maybe 500 nanometers, right in our energy range right here. So that's a very tight confinement of a light wave to a small volume with small polariton wavelengths like this. So I told my student Braden, go and hunt for this, look very closely. And so what he did is he took nano-optical spectra across the edge of the membrane, on very, very small length scales, 10 nanometer pixels each. And this is an example of the infrared absorption as a function of position when the probe is stepped away from the edge of the membrane, showing a mode here that is absorptive that looks exactly like a polariton mode. And so here's a function of distance from the edge. The absorption is either happening close to the edge or is happening far from the edge. And the dispersion of this absorption is indicating the wavelength, actually, of the polariton. And I just want to remind you the mechanism here is something like that echolocation of a light field, a polariton light field that's launched by our probe and then reflects off of the edge and then comes back, giving rise to some kind of interference pattern, which is what we're probing here, which tells us what the wavelength is. So I told my student, okay, go in even further and take spectroscopy at every pixel close to the corner of this tiny, tiny little membrane. And what you can see here is that the light field is actually confined right to the corner of that membrane, as you can see here in the absorption contrast, the infrared absorption contrast. And this little fringe that works its way from the outside to the inside is in fact the polariton mode. So this is exciting because not only do we have the properties of this membrane that come in the bulk form, but now we also have polaritons in this membrane because it's a two-dimensional material. So just to round that out, I told my student Braden to measure the dispersion of this polariton as a function of thickness of the membrane. And we can tune the wavelength, or equivalently the wave vector, of this polariton. Doing experiments like those on different thickness membranes, we find that we can tune the dispersion of this polariton by about a factor of 5 to 10, just by changing the thickness of the membrane. And by putting the membrane on different substrates, we can also change the wavelength of the polariton in this way, whether putting it on a silicon substrate or a silicon oxide substrate, tunes the polariton wavelength by something like a factor of 1 to 3. And it was not entirely clear what's the reason for all of this, why we're able to achieve this sort of tuning. So in order to understand, we can zoom out from that predicted dispersion and see a wider picture. So here are some data points right where the prediction says there should be a polariton. But the truth is the prediction says that there's another polariton down here as well. So I want to talk just for a moment about why that might be the case. So our membrane is a cute fellow because it's a two-dimensional version of a three-dimensional material. So it actually has two interfaces. It has a top interface and it has a bottom one. Now the polariton is a light field that's confined to an interface. So there's a top polariton, but there's also a bottom polariton. And to start with anyway, they should have the same energy, the top polariton and the bottom polariton. But the truth is they should interact with each other through their electric fields. And in the same way as if you have two energy levels in an atom that are degenerate, but then they interact with each other, we should expect a mode splitting. So in this case, we expect a mode splitting into a bonding orbital or a bonding polariton and an anti-bonding polariton. And so with this very simple picture, if we now measure this splitting as a function of momentum, what we expect is a dispersion that looks like this, with a lower branch and an upper branch. So the bottom would be this omega minus, and the top would be this omega plus. And the splitting between them can be controlled not just with the thickness of the membrane, but also with the permittivity of the substrate. So this was a prediction that's now borne out with our measurements here. And one quite remarkable thing about polaritons in these engineered 2D membranes, the bottom branch here looks similar to that for our graphene plasmons. There's a group velocity that's greater than 0. And I'll mention what the group velocity means in just a moment. In the anti-bonding mode, though, if we look at this region here, the slope is actually going downwards as a consequence of this splitting. Here, the group velocity is negative. What does a group velocity mean? And especially what does a negative group velocity mean? Well, here's an example of a situation where the group velocity is negative, but the phase velocity is positive. So although the phase of the light wave for this polariton might move from right to left, the energy content will move from left to right. So this is a very oddball situation where by making this membrane into a sufficiently thin layer and having interaction between these two polaritons, we generate this anti-bonding polariton. And that anti-bonding polariton naturally has a negative group velocity. So this negative group velocity is not encountered normally in nature, but it's an ingredient for manipulating light fields to very acute effect, like has been suggested by John Pendry back in the year 2000, where if you take a negative dispersion material, that is a material with negative group velocity, and you put it next to a material with positive group velocity, if you send a light wave from one medium to the other medium, you will end up with an automatic focusing of the light field. And this is called the Veselago lens. And there's a bunch of opportunities for manipulating light fields in the nanoscale by combining these different dispersive materials together in a small package. So we're excited then about the opportunities of using the optical properties of these membranes to manipulate light fields to do this so-called transformation optics at the nanoscale. The idea is with these engineered membranes, we can manipulate light fields in ways that were difficult or even impossible in 3 dimensions. So I want to conclude, because I've taken enough of your time, and just give you a flavor of what the future looks like. And the future is bringing this technique to lower temperatures. And this is based on implementing the near-field optical microscopy technique inside of a vacuum chamber and cooling our sample down with a cryostat. And so this is just a quick sketch of a microscope that's now operating in my laboratory, which is quite exciting to take these investigations of quantum materials down to lower and lower temperatures. So this is called cryogenic nano-imaging. And this is work of many students in my lab, including Liam Thompson and William Cho. Here are some examples of preliminary pictures of the setup as it's operating to do these investigations at low temperatures now in my laboratory. So it's a very exciting time to be working with scanning probes and also with light fields to probe the nano-optics of these quantum materials. And so on that note, I want to conclude, and thanks a lot for your attention. And I'll be happy to take your questions, of course, in the Q&A session. So thanks a lot.